Okay, let's start. All right, hi guys. I'm sorry I couldn't do videos this week. I really apologize. I had exams and I really appreciated all the support that you guys sent me. All your emails were really much appreciated. I really helped, and as well for you guys being really understanding with my slower response to emails. I am quickly getting through these videos. A lot of people gave me feedback that they would really just have me put up the answer and then talk through the answer. So that's what I'm going to do for these next two videos that I'm going to release and see how that goes, and then ask for your guys' feedback on that and see if that's more aligned with what you guys would like to see in these videos. If you're doing this quickly for an exam, for the final exam, good luck, and let's get started. Okay, so some things I wanted to note about a standard cell really quick. Selecting an oxidizing agent. This is meaning that you are selecting the thing that's going to be reducing, right? Because oxidizing agents are reduced and reducing agents are oxidized. And this means that we are looking for the thing that is the better electron acceptor. So to kind of relate it back to acids and bases and things, we are literally looking for the thing that is good at accepting electrons, aka more positive. And something that is more positive is going to want to become more negative and therefore gain electrons and then be the oxidizing agent. So there's ways to kind of relate that back to acid-base equilibria if you're not too sure about that, but the first thing I would do is kind of go back through and say, okay, can I relate these as electron acceptors and electron donors? Can I make them into Lewis acid, Lewis base kind of things? And then relate that further. When you're identifying a redox reactions have to have both reduction and oxidation happening in them and a transfer of electrons overall. And so that means that if I have zinc being oxidized to zinc 2 plus 2 electrons, that is only an oxidation half reaction, and that's why we call them half reactions, but it's definitely not a redox reaction because there is no balance to the overall reaction. And then finally, when you are balancing these types of reactions, you're going to make sure that you are balancing the electrons, and I'm going to show that a lot more in detail in the next video with neutral conditions, acidic conditions, and basic conditions. So if that's what you were looking for in this video, that's in the next video, so go look at that one. All right, so quickly getting into this past homework that you guys have already turned in, and I know you're like, Victoria, this isn't helpful now, so you can skip ahead in the video if you want to help on this week's homework, but this one was just something I wanted to note about this that someone brought up that was a good question. So the first thing I want to note is when I read through this equation, I'm at 25 degrees C, so I already know that I'm going to be at 298 degrees Kelvin. I read through this and I'm like, okay, I've got 2B, so I need to make sure that when I'm writing out my equilibrium constant at pressure, Kp, that I have the pressure raised to the power of 2. And then it gives me my pressure, so I'm going to plug those in, be sure to square this one, and I get this as my K value. Now, note that these are all in pressures, and someone asked me, okay, so if this is Kp, what if I have to go to Kc, or when would I have to go to Kc? And I was like, oh, that's a very good question. When do you have to go to Kc? Well, when you'd have to go to Kc is if you had a mix of different reactions here. So these are all gases, right? So these are all going to be in pressures, in this case in bars. But what if you had, say, A was aqueous, or C was aqueous, or A, C, and D were all aqueous, and this B just so happened to be a gas, like chlorine gas or hydrogen gas or who knows. Then you would have to convert, and I would consider converting this into a overall concentration, and that means that what I found here would need to go to Kc. So that's kind of like a reason that you would need to convert between them. And there is an equation for that, and you will be given that on the exam if you need to do that, so don't be too concerned. And then it's going to ask me what the standard change of Gibbs free energy is, and I'm like, okay, Gibbs free energy, standard, this equation is definitely the equation I'm going to use. This is a very important equation. I would say know this equation by heart, but it will be given to you, but do know it. And also you have your notes, so it's basically given to you anyway. This is my R value. I'm going to note that my R value is in joules per mole, and that means when I plug in all my numbers, this number here is in joules per mole. And we usually convert this into kilojoules per mole, and that is because enthalpy is normally in kilojoules per mole. You'll also note that entropy is usually in joules per mole, so be sure that you are able to confidently go between joules per mole and kilojoules per mole between all of them, simply because overall you'll note that there always is that nice trick answer that is if you didn't convert them. So please be aware that if you either don't see your answer or you do see an answer but you're like, this seems big, make sure that you double check the units and make sure that it's kilojoules per mole or joules per mole. Okay, quick mental exercise, like pause the video, take a deep breath, in case you're, this is for like if you're studying for the exam, just deep breath, relax, everything's gonna be fine. Okay, writing an overall balanced reaction. What I love about these is they're actually very fun and a very quick little tidbit that I like to do. So basically what I do is I take the charge of the top reaction and I multiply it by the bottom row. I take the charge of the bottom reaction and I multiply it by the top row. Note these all have imaginary ones because this is 1 plus. So this is imaginary 1 plus here. And the way that I double check that I've done this correctly and I've multiplied everything correctly as I go through here. Okay, 1 times 0 is 0. 2 times 1 plus is plus 2. Good. Okay, 1 times 2 plus is, again, plus 2. And 2 times 0 is 0. Great, this balances. This equation is very, very similar, but I just kind of wanted to show that it does work for multiple things. So again, you just multiply this charge up here by this bottom row, multiply the bottom charge here by the top row, and again, we get the same thing. 0, 2 plus, 0. Same idea, just a bit trickier because now we have two numbers and we want to make sure that we multiply that all the way through. And the only way that these things really get mixed up, I think, and students get mixed up in general, is that they forget to multiply the solids by the coefficients. And I think the only reason for that is just that it's because it is 0, right? So we kind of forget them, but do double check that when you are looking at the overall balanced reactions that you find the one that has the coefficients correct in front of the solids, because when you think about it in this reduction reaction here, this is 1 to 1, or in this oxidation reaction, this is 1 to 1. But if I multiply the top row by something, that means the number of electrons here needs to also, will technically also be multiplied, and I need to make sure that they cancel, which is what I'm alluding to, but these are all in neutral conditions, and I'm going to show you that in a later video. So I'm not going to go too into depth with that, but this is how I do it when I don't need to worry about it. Okay, so galvanic cells. I'm going to take a swig of coffee. Okay, galvanic cells are fun. I think what people get confused about is they like to forget that they're pretty straightforward. And by straightforward, I mean that I go through and I see that they're all 1 molar, so there's no mole change. So I don't have to worry about that. And when I'm calculating the standard potential for this, I basically just have to make sure that it's a positive cell potential. Positive cell potentials are what we need to be spontaneous. And then I need to make sure that I remember, this is an acronym I used to remember it, ANOX and a red cat. ANOX, oxidation happens at the anode, and reduction at the cathode for red cat. And then I put down the half reactions. These would actually be given in your standard list of potentials, but I don't want to go and flip through things. So this is what I got from the table. Now, this overall is E cell equals the reduction potential at the cathode less the reduction potential at the anode. So you are not flipping sign here. A lot of people were like, I want to flip sign. I'm like, you're flipping sign if you're thinking about it as the electron potential of the reduction less the the cell potential of the oxidation, and then you flip signs. I don't do it that way because I don't like flipping signs. It makes my head hurt because I'm like, is this what I'm doing? I don't like doing it. It gives my brain a headache. Instead, what I like to do is I like to do cathode's reduction potential minus the anode's reduction potential, and when I do that, I basically just have to plug it in until it gives me positive numbers, right? So I plug in, say I plugged in negative 4.03 first, less negative 0.28. If I were to do that, I would get a negative overall number, like negative 1.6 something or whatever. But if I do negative 0.28 less negative 0.403, I actually get positive 0.327. So then I know, okay, I've done this correctly. And the other way to kind of do like a mental, like, does this make sense check, is that, okay, cathode is where reduction happens, so gaining of electrons is happening. And because this is more positive, right? Because if I think of a number line, 0's here, negative 0.2 is here, and then negative 0.4 is here. So this is technically more positive than 0.4. That is the one that is going to want to gain electrons to become closer to negative 0.4. Same thing, anode oxidation loss, so it's becoming more positive, right? So if I look here, this is more negative, and therefore it's trying to get closer to negative 0.28. And therefore it's going to try and lose electrons to then become more positive. All right, another quick mental health break. We take a big little mental health break here. Okay, And then this is kind of the same thing. I wanted to show another example with this, and that and kind of go through this a little bit more in detail, just to show again the same idea. I have a negative. These are taken from a table, and I have this potential here, and then all you really have to do is plug them in. But another way to think about it is that, okay, the reduction potential. If I look at the reduction potential, this is more negative, and because this is more positive in this case, and because it's more positive, it's then going to want to reduce to become more negative and closer to this negative 2.83. The negative 2.83 is going to become more positive, and therefore it's going to lose electrons in order to become closer to negative 0.4. But again, you can also just plug it in until you get a positive number. Either way works. Up to you. Okay, this is again another quick one that was like balancing equations, and I don't really want to go through it too much in detail, but I do want to note, okay, this is the given equation. To balance it, I have to add electrons, and because I know that the electrons are on the reactant side, it means that they were gained in the reaction, and therefore it is reduction. And then this is how we balance it overall. Right? Very, very simple. I wanted to show this just to kind of go through it in detail, because in the next video I kind of just speed through it. Okay, and the final thing I wanted to show you is using cell potentials and things, because these are quite tricky. But the thing that I want to note here is I see my reaction, and I see that my Fe2 plus is a reactant and my Mg2 plus is a product. And so I do know that Q is in here, and Q is a reaction quotient. So already when I do my concentration of products over reactants, I'm going to do 0.110 molar divided by 3.5 molar. And that's going to get me my Q. Cool. I know R, I know T, and I know F. So here's the equation that you're going to be given. And then I would always say that since you know F and you know R, and you usually know T somewhere, this is given at 47 degrees C, so we do 47 plus 273. I would already plug those in and multiply it out to get you to this section. I would already go through it like this to get you to where you're supposed to be. And then I plug in my Q, done that here, great. And then I know that, okay, here I need to get E standard, a quick little cathode minus anode. Cathode minus anode gets me 2.92 overall. Again, I take, I plug these through and I find, okay, which one's more negative, which one's more positive. And, oh, whoops, this is backwards and should be flipped. These should be flipped. Oh, wow. We'll work through that, but let me erase this actually. So basically what you're gonna do is, I did this the other way. I did this where it's not cathode, but it's what's being oxidized, or what's being reduced, sorry, is being then oxidized. And I don't know why I picked to do it this way, but maybe to show it a different way, but then I didn't change these. Odd. Anyway, and then you'll get 292. I'll go through this math later. Usually you're given the standard E cell, and I've gone through them earlier, and I'll post the fixed slides later. But this is 292, 36, and let me do the math. And yeah. So I put in the standard E cell, and then I know the rest. I know that it's 2 electrons being transferred. I have 2 electrons here from my iron overall, and the 2 electrons in magnesium. So I do know overall 2 moles of electrons are being transferred. Great. And then I know my Q, so I plug that in and I get 196. Okay. So that is it for this video, and I will see you guys in this next video that's going to go through balancing things with acidic, basic, and neutral concentrations with a few steps to get that started. Okay, let me exit out of this.